Okay, we're going to continue on here, chapter 3. We've been talking about bonding last time. And we really talked about the two different types of bonding. There is ionic bonding. And that is, again, always really between a metal and a non-metal. And again, remember that there is no sharing of electrons here, but we do get the transfer of electrons, again, from the metal to the non-metal, resulting, as we talked about, as the metal becomes positively charged ion and our non-metal becomes our negatively charged ion. And again, it's that electrostatic attraction between those two that basically hold that together. On the other end there, we also have covalent bonding that we also talked about. And in covalent bonding, that's usually between two nonmetals. And again, because of the periodic transit they have, they really do not want to get away their electrons. They really want to hang on to theirs. They also want to grab maybe more electrons as well. So we do get sharing of electrons here. And as we talked about, there's really two types of sharing that occurs. There's really equal sharing, which is considered a nonpolar bond. And there's also unequal sharing of electrons, which is considered a polar bond. The result of an unequal sharing of electrons in a polar bond results in really the electrons at one side of the bond versus the other. So example, we looked at HF, and because F is more electronegative, what will happen in that bond between hydrogen and fluorine is that the fluorine will really kind of pull those electrons closer to its side than the hydrogen side. The results of that, again, gives us this dipole arrow, which always points to the more negative side of the bond. The other side points where it kind of makes a plus in the back to the more positive side, creates a partially negative charge on the fluorine and a partially positive charge there on the hydrogen. And that doesn't happen in a nonpolar bond. In a nonpolar bond, we have basically equal sharing of electrons. So sort of, again, like a neutral sort of bond, if you will. There's really no positive side or negative side to that bond. What determines that, again, is really the electronegativity. And again, we could do the change in electronegativity values. And we could use those values, which run from 0 to 4, 4 being, again, the most electronegative. And again, when you have a change in electronegativity values of anywhere from 0 to, try again, 0.4, that's going to be considered a nonpolar bond. Remember that, as we saw, if you really have an electronegativity difference of 0, it is sometimes also referred to as a pure covalent bond. It's still nonpolar. It just means you have really perfect equal sharing of those electrons. If you're kind of above there, 0.4 to below 2, that is really your polar range there in terms of difference in electronegativity, which means we would not expect, again, those electrons to be shared equally. And generally speaking, if you go above 2, you're getting into really the ionic sort of situation. A couple of things we talked about in terms of using electronegativity values. If you have them, obviously you can use them. In a lot of cases, you may not really need the actual values. You could use just the general trend in electronegativity, which is up and to the right is more electronegative, left and down is least electronegative. That works really well for things that are in the same period on the periodic table. If you're comparing two things on the same period of the periodic table, and one is obviously further to the right, for example, than the other, then it's definitely going to probably be a polar bond. And again, you probably don't even really need the values to do that. Also, if they're in the same group, the two elements, again, the guy further up would be more electronegative and probably should result in a polar bond. So there's a lot of places where you can, in most cases, make a pretty good guess in terms of whether or not it'll be polar just by using the general trend. There are some things like we talked about, for example, again, carbon and sulfur, which again are diagonal on that periodic table. So you got carbon and then sulfur, so kind of down and over that diagonal. And they do sort of cancel out their electronegativity differences. So It is possible, again, for two different elements to really have the same electronegativity values. Again, one being further up and then one being further to the right. So again, that sort of difference cancels them out, and you can't get a nonpolar bond in that particular situation. Any questions on any of that there that we talked about, I think, last time? We also drew Lewis dot symbols, I think, for ionic compounds at that point. And remember that when you do draw it for ionic compounds, you do need to include the charges. So in a situation like this, we would get that transfer of electrons over, and that would result in sodium becoming positively charged and chlorine gaining that electrons and becoming negatively charged. As we talked about as well, again, remember that the whole point of bonding, both ionic bonding and also covalent bonding, is really to achieve the same electron configuration as the noble gases. Again, not become the noble gases, but achieve the same electron configuration as the noble gases. And in ionic bonding, the way they do that, as we saw, is essentially the metals will lose electrons, and what that does is basically back them up to the noble gas that comes right before them on the periodic table. The nonmetals are able to accept those electrons, and that allows them to move forward on the periodic table to the next noble gas, and they both really achieve that noble gas configuration. As we touched upon, when we were talking a little bit about covalent bonding, that also occurs, except that obviously is not transferring electrons that occur in that situation. They achieve that by sharing electrons. So by sharing electrons in a covalent bond, they're able to, again, pretty much hit the octet rule, which is 8 electrons around them. And again, that allows them to be just like the noble gases and be very happy. The one really important exception to that, again, is hydrogen, that only needs to get to 2. So it could be like helium, and again, that sometimes refers to the duet rule. So that 8 number and obviously the 2 number there for hydrogen, really important in terms of covalent bonding. But it's the same overall idea of really the purpose of the bonding is for them to achieve that noble gas configuration in terms of their electrons. Any questions on that? I think that we also talked about that. All right. So we laid it up there, I think, right here at actually talking about the steps that you should follow when you draw Lewis structures for covalent compounds. So we obviously drew them for ionic compounds earlier. When you do covalent bonding, these are really the steps that you should follow, and it really should lead you to a fairly good sort of picture when you're all done. You again do not want to do it in any type of piecework or anything like that, which is what sometimes people do. They take each of the individual elements with their valence electrons and then try to figure out how it all kind of comes together. And if you do sort of the piecework approach, usually what would happen is you'll end up with really the wrong structure, too many bonds, not enough bonds, and those type of things. But if you sort of follow these steps here that we're going to talk about, you should really end up with a pretty good picture at the end. Maybe not the perfect picture, and we'll talk about how you can determine that a little bit later, but you'll end up with a pretty good Lewis structure to do that. So it really all starts with how everybody is sort of connected together, and you want to think about sort of a skeletal sort of structure as to how it's put together. And there are a few things that can help you decide sort of where things maybe should end up. The first sort of major rule is usually in the center, and the center atom is usually the least electronegative atom. So usually occupying that center spot is the least electronegative atom. And I would say in a lot of cases, not all, but in a lot of cases, a lot of things are just attached to the central atom. It is possible in several molecules or compounds that you have multiple center atoms, but usually a lot of times what we deal with, you kind of have one center atom and maybe everything else is attached to it. But it can obviously have multiple center atoms. Once you figure out which one should be in the middle, and obviously common sense also plays into a role. If you have like one element and like 3 of some other element, probably the one element's in the middle, everybody else is attached to it. That also means because of that, we should never find hydrogen or fluorine in the middle of an atom. And again, because hydrogen should only have 2 electrons, so if it's in the middle, it's going to have too many electrons, so you can't put it in the middle. And then fluorine obviously is the most electronegative atom, so it should not occupy the center. So those guys really should always be on the outside. And we talked about yesterday, just a reminder, pretty much in your Lewis structures, yeah, that's what hydrogen should look like. Again, no dots, no double bonding, triple bonding, or anything like that. Once you sort of have the arrangement of how everything should sort of be put together, probably the most important thing in terms of drawing Lewis structures is the next one, and that is counting up the total number of valence electrons. So this is the total number of valence electrons in the entire molecule. And you basically go to the periodic table, and obviously, as we've been talking about, the very quick way to figure out valence electrons is it's equal to the group number. So you add up all the valence electrons that are there. Now, if you are drawing something that is an ion, you do need to adjust your count in terms of electrons. And a reminder that if something is positively charged, that means it has lost electrons. So you need to subtract that many electrons off from your picture. And if something is negatively charged, then obviously you need to add however many electrons that would be to your picture or your number, basically. And the importance of that number is that is the exact number of electrons that your picture needs to have when it's all said and done. You cannot have any more or any less than that. It's got to hit that number on the nose. We also sort of think of electrons, and a good way to do it, as I was mentioning a second ago, is to think of these electrons as not necessarily belonging to anybody, but you need to kind of distribute the electrons around to everybody in that picture, rather than like sometimes people get hung up on piecework, like, hey, nitrogen has 5, you know, it needs 3 and all that kind of stuff. So, you know, you want to think of the total number of electrons as just needs to be properly distributed basically to everybody in that Lewis structure picture. The next thing that you want to do is, once you got sort of the arrangement and you got the total number of valence electrons, for the most part, you want to make one single bond from the center atom to each of the outside atoms. So once again, we talked about you don't really want to double bond or triple bond out of the box. You just want to kind of make a single bond from the center to each of the outside atoms. At that point, remember, if you use lines, which a lot of people do, myself included, or if you use dots, one line, right, represents, again, a pair of electrons or 2 dots. So for every line, obviously, that you make a single bond from the center to the outside, you should subtract 2 off of your total from the previous number that you had. That means in most cases, you will have some electrons left over after you make the single bond to each of them. The next thing that you should do is take those leftover electrons and you should put them on the outside atoms in pairs of electrons as dots. So you should fill up all the outside atoms with pairs of electrons until each of the outside atoms basically reaches the octet rule. Obviously, if it's hydrogen on the outside, no dots, you just skip over it. But all the other elements, you should put dots around it. So now if you made your single bond from the center to the outside, you put your dots on all the guys on the outside, and you still have electrons that you need to put into your picture. It is at that point you go to the center atom and you put those electrons on also as dots, so as a pair of electrons. So it's kind of single bonds to the outside, pairs of electron dots on the outside, still leftover electrons to the central atom, and you put it on as dots. At that point, you probably should be out of electrons if you're putting some dots on the central atom. The last thing that you want to kind of do in your picture is to make sure that the octet rule has been met. So you want to make sure, obviously, everybody has 8 electrons. And if somebody does not have 8 electrons, it really is that point where you want to kind of fix it. And the way that we try to fix it is, if somebody does not have 8 electrons, we then will go and try to make a double bond to fix the situation. And once we fix the situation, hopefully with a double bond, you should be good. If the double bond doesn't fix the situation and there's a possibility perhaps to make another double bond, then you would make another double bond. If there's not an opportunity to make another double bond after you do the first one, then you should go to a triple bond. So again, in most cases, it's a good idea to save double bonds and triple bonds to sort of fix a situation where somebody has not met the octet rule. Again, don't double bond or triple bond out of the box. Any questions on that there? All right, so let's see this in action perhaps here. Let's take a look at this one and we'll do it here together. All right, so we have NF 3. So the first thing that we might want to do is figure out the total number of valence electrons. So if we look at the periodic table, nitrogen is number 5 there. So there are 5 valence electrons for nitrogen. There are 3 fluorines, and each fluorine is group number 7 on the periodic table, which means it has 7 valence electrons. That's a lot of math there. 26, we'll go with it without the calculator. There we go. All right, so that number again is really important because that is exactly where we need to end up when we're done here. So let us do it here. We got nitrogen and fluorine. We really have 1 nitrogen and 3 fluorines. So in most cases, obviously, nitrogen should go in the middle. Nitrogen should also go in the middle because if we look at electronegativity, obviously, fluorine is more electronegative than nitrogen as it's further to the right on the periodic table. And it is the most electronegative element you could have. So the sort of skeletal arrangement should be nitrogen in the middle. And like I said, a lot of things that we draw pretty much will be connected to the central atom, but you can have multiple central atoms if you wanted to. So we do want to arrange our fluorines around the nitrogen. And in this particular case, we could put the fluorine on the bottom there, or you could put it on top. It really doesn't matter. So you could go either way on that. Once we have the fluorines in there, the next thing that we're going to do is make 1 single bond between the nitrogen and the fluorine. And at this point here, we have used up 2, 4, and 6 electrons, 2 for each line that's there. So if we subtract off 6 there, we got like 20 more electrons that we need to put onto this picture. To do that, we are going to start on the outside atoms until we fill them up basically with 8. And we don't have any hydrogens on the outside there, so we don't have to worry about it. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have pretty much filled up everybody on the outside. I have used a grand total right now of about 24 electrons, as I just put 18 on there. And I have 2 electrons basically left at this point. The next 2 electrons should go on the central atom. And again, here it should go on as a pair of electrons. Now, my picture here has 26 total electrons, and everybody here does meet the octet rule. We got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and the nitrogen 2, 4, 6, and 8. So we do have obviously 8 electrons around everybody. Everybody has met the octet rule, and everybody is happy, I hope, at that point now. Any questions on that? All right, so why don't you try one here? Why don't you do instead of the one you have, why don't you do this one first? Let's just do NO3 minus. All right, draw the proper Lewis structure, see what you come up with here. Okay, let's take a look to see how you're doing. So we'll start with our valence electrons. So here we have 5 for our nitrogen. We have 3 oxygens. Oxygen from the periodic table is group number 6. And here we do have a negative charge, which means it has gained electrons. So we do have to add that in to our total here. Again, otherwise we are going to be off. So that's like 18, 19, 24-ish there. Seems like a good number. Once again, here we have nitrogen and oxygen. And if we look on the periodic table there, nitrogen is to the left of oxygen. And that means it should be the least electronegative atom. Also, there's only 1 nitrogen and 3 oxygen, so probably should go in the middle as well. So we're going to put our nitrogen here in the middle. We're going to do some oxygens around it. Once again, you could do the oxygen top or bottom. It really doesn't matter. We're going to make our 1 single bond to each of the oxygens here. So single bond, and single bond. And that, again, is a grand total of 6 electrons that have been used up. We got 2, 4, and 6 there. That's like 18-ish, I think, more to go after we subtract that. We're going to put that on the outside first here. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 here. At that point, I have now put on there all 24 of my electrons. Is everybody good here? It is not, and the nitrogen is not good, right? Nitrogen has only 6 electrons around it, right? Everybody else is okay. The oxygens are okay and stuff like that. So we do need to fix it. And in this case, to fix it, can I just do this deal and just kind of put some electrons on there? I cannot, right? Because now I have 26 electrons, right? So that is too many electrons. So what we want to do now is move to what we were talking about. We have distributed really all the electrons that are present, but we need to now perhaps make a double bond to fix it. In this particular case, all the oxygens are really the same, so you could double bond up anybody that you like. So we do want to try to make a double bond to fix it. And if I just do a double bond like that, is that okay? That is also not okay because the same thing just happened. I now have 26 electrons and my oxygen up there now has 2, 4, 6, 8, 10 electrons, which again seems more than 8. So that's not so good either. So really when we make a double bond, or even if we are going to basically make a triple bond, what we actually need to do is actually bring a pair of electrons, those non-bonding electrons, in to make those double bond or even a triple bond if you needed to go that far. So really what we're going to do here is we're going to take a pair of electrons, and it really doesn't matter which oxygen in this case you do it with or which pair of electrons. So I'm just going to take those pair of electrons, and basically we're going to move them in to make that double bond. And when we do so, we will end up with something that looks like this. We have now double bonded up over here. And we have our oxygen here. And we also will put a little bracket around it and the charge on the outside since it is an ion. So usually you bracket it up, put the charge on the outside. What that now has done is a couple of things. It has really fixed our problem in this situation. Our nitrogen now has 2, 4, 6, 8 electrons. Each of the oxygens on the outside have 2, 4, 6, and 8 electrons, 2, 4, 6, and 8 electrons, 2, 4, 6, and 8 electrons. So everybody now has met the octet rule. We still only have a grand total of 24 electrons, which is what we need when we draw these things. Any questions on that there? Now, if you wanted to, because all of these oxygens are basically equivalent to each other, we could have just as easily done the same thing to, say, the oxygen on the right. And if you did that, you would end up with a picture that looks something like this. And you could also, again, done it to the guy on the left there, the oxygen, and you would end up with a picture that looks like this. All 3 of these structures are related to each other. They are what are referred to as resonance structures, and a lot of times they are separated by this arrow that kind of heads in both directions. These are resonance structures of each other. And basically a resonance structure develops in this sort of situation where you have multiple places where you could make that double bond. And the real truth is the double bond electrons here that we brought in to sort of make the double bond, they're delocalized, which means that at any given point in time, you know, they may be kind of hanging over here at this guy. They may be over here at this guy, maybe over there at this guy. So the true sort of structure of that NO3 minus is somewhere between all 3 of those Lewis structures, but you could draw an equivalent Lewis structure for each of those, and they would be considered resonance structures. So simple way to figure out resonance structures, really any other options to make double bonds, you basically could draw a similar type of structure. And again, because those electrons are basically moving around from one place to the next, it could be any of those 3 things or in between any of those 3 things. Any questions on that there? You do not necessarily have to draw the resin structure all the time unless it's obviously asked you to do so. But there are definitely situations where it can come up. Any question on those steps there? All right, let's practice some here. Well, all right, so I think you have CO3 2 minus maybe on that one. So why don't you do that? Why don't you also draw HNO3 minus HNO3 nitric acid? Let's do SO2. Let's do a little HCN. Let's do NH2 minus. And let's do N2. And SH2. Actually, you know what? Let's do we'll do that one. That's fine. Let's do CO2 instead of CO3 minus. So let's do that one. Yeah, let's take a look and see how you're doing. So we'll start with the nitric acid, HNO3. So total valence electrons here, we got 1 for the hydrogen, we got 5 for the nitrogen, we got 3 for the oxygen. It's like an 18, 19, 24 situation. As I mentioned before, in this case, the hydrogen actually is attached to an oxygen in this case, and nitrogen still being least electronegative of the bunch, should go in the center. Again, hydrogen cannot go in the center either. So the sort of arrangement that you would have here would be something that looks like this, with a hydrogen attached to really one of the oxygens. It doesn't matter really which oxygen you attach it to, but it does need to be attached to one of the oxygens. In this case, we will still do our normal situation here. We will connect pretty much everybody up with a single bond. In this particular case, you could also see that we actually do have more than one central atom. So we have a nitrogen and we have the oxygen there that's also considered a central atom. And again, it does happen, obviously, in this situation. We really still do follow sort of the same procedure. So we did 4 single bonds, so that's 8 electrons. So we got 16 more to go. So we're still going to kind of work from the outside in to distribute those electrons. Should I put any dots on my hydrogen? I should not, right? So it is done. You shouldn't do anything else to that hydrogen. So we would still put some dots over here on this oxygen. So that's 2, 4, and 6. We would also put some dots over here, 2, 4, and 6. At this point, I have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. I still have 4 more to go. Really, the next sort of outside atom, if we look at the nitrogen as sort of the center atom, is going to be that oxygen. So we would put it there, and it can take some electrons. It also would go on as pairs of electrons until it gets full. At that point, I have now put on there 24 electrons, I believe, if I count up all the lines and the dots. We want to make sure that everybody is good in terms of the octet rule. Hydrogen is obviously good. Is everybody else okay here? The nitrogen is short still, right? So nitrogen here only has 6 electrons to it. It has 3 lines, which means it's got 6 electrons. So once again here, we do need to fix this by making a double bond. And in this particular case, we actually have really kind of 2 options is probably the best approach. We could either perhaps double bond here or double bond to that oxygen. In most cases, you probably would not double bond over here to this oxygen. That's actually what makes it an acid. That's the hydrogen that comes off to make it an acid. So you typically would probably not double bond in that situation. So we're going to double bond. And again, you could choose either one. Just like we did previously, we're going to take a pair of electrons, for example, and bring them into double bonded up. And if I do that, I will end up with a picture that looks like this. We also could draw a resonance structure because we could double bond to this guy, and I'll do that in this case. I'll take those guys in to do it. And if I did that and double bonded over to the left-hand side, we will end up with a much crowded picture here. It looks something like that. Get rid of that arrow. It's just not so crowded. So this, either one of those really would be a proper structure for nitric acid. And again, really does have two central atoms, the nitrogen here and the oxygen, considered basically two different central atoms. Any questions on that there? Yeah. What's that? It does. So by doing the double bond, it gets us to the octet rule. So previously to that, this did not have 8 electrons. The nitrogen only had 6, right? Those 3. By making the double bond, this nitrogen now has 2, 4, 6, and 8. This oxygen 2, 4, 6, and 8. Hydrogen has just 2. This oxygen on top 2, 4, and then obviously 6 and 8 there. And this oxygen 2, 4, 6, and 8. So they all have 8 except for hydrogen. And that's why we did need to go to the double bond in this situation to get it. Other questions? All right, let's take a look at the next one, which is SO2. So we'll go with that one next. Our electrons here, sulfur group 6, 2 of group 6 for the oxygen, going to be 18 valence electrons in this case. Once again, sulfur and oxygen are in the same group on the periodic table. Oxygen is higher up, which means it is more electronegative, and sulfur would be least electronegative. So it is the sulfur that should go in the center here. So a little sulfur action, some oxygens on the side. Going to do the same thing. We're going to do a single bond to each of them. I have now used 4 electrons. Going to distribute our oxygen, our non-bonding electrons to the outside. So that's 2, 4, 6, 8, 10, and 12. At this point, I have actually put on 16 electrons. That means there's still 2 left, which means they should go to the center as non-bonding electrons. That's how you get those there, by the way, and not Google it and put 2 double bonds on both sides and get the wrong structure. Yes, so that is the right way that you do it. At this point, when we do look at it here, we do see hopefully that sulfur again is a little short, right? So it's got only 6 electrons. The oxygens are good. They have 8 electrons on it. So we're going to do our same thing here. We're going to fix it by making a double bond. Same deal. You could choose either oxygen in this case. We're going to bring it in to make that double bond, and that will get us this guy here. Looks like this, if I remember what I was going to draw. And again, this one also, we could draw a resonance structure where you just did the double bond on the other side there. And now in this situation, everybody will have 8 electrons around it. The sulfur here, again, 2, 4, 6, and 8. This oxygen, 2, 4, 6, and 8. This oxygen, 2, 4, 6, and 8 as well. So again, we meet the octet rule here by making the double bond in this situation. Any questions on that one there? All right, then let's take a look at the HCN. I'm gonna flip the page so I got a little bit more places to write, I think. HCN. All right, so same thing. We got 1 for our hydrogen. We got carbon is 4 there, plus nitrogen is 5. Looks like 10 valence electrons. In this case, clearly hydrogen shouldn't be in the middle, and now we're looking between carbon and nitrogen. And again, they're in the same period on the periodic table. Carbon further to the left, which means it's the least electronegative. So it should be the carbon in the middle. So sort of this arrangement happening. And in this case, same idea. We're going to single bond it up. So that's a single bond. That's a single bond. That is 4 electrons in this particular case. We then will have 6 electrons to go. Outside, we are not going to do anything with the hydrogen because it is fine. So that brings us to the nitrogen on the other side. We will do 2, 4, 6, 8, and 10 electrons at this point. We have used all 10 electrons. Hydrogen's good. Carbon in the middle is not good, right? It's only got 4 electrons, 2 on each side there, if you will. Nitrogen's okay. It actually does have 8 electrons. In this case, we want to try to fix that by making a double bond. And our only option really is to take it from the nitrogen here. So we're going to bring those in to do so. That's going to give us an HC double bonded nitrogen. Did that fix the problem in this case? It did not. It got carbon a little bit better. It's up to 6, but it still needs to get to 8. So at this point, there's really nowhere else that we can make a double bond. So now we should then proceed to a triple bond. So triple bond works the exact same way. We're going to take those electrons in to do so. So we'll grab a pair of electrons there and bring them in to make the triple bond in this case. And then we will end up with something that looks like this as our structure. Now looking at it again, the hydrogen has 2 electrons. By actually making a triple bond with the nitrogen, the carbon in the middle now has 8, 6 from the triple bond and 2 from the single bond. And the nitrogen still has 8, again, 6 from the triple bond and the 2 lone pairs that are there. Question on that one there. Next one was NH2 minus. All right, so next one is NH2 minus. All right, so we got 5 here from nitrogen, 2 times 1 for the hydrogen. Once again, here we do have a negative charge, which means I need to actually add an electron, right? And we're going to add 1 electron. That's going to be like a 7 and an 8. In this case, clearly hydrogen should be on the outside, nitrogen should be in the middle. And we'll do a little nitrogen hydrogen move. Going to do a single bond here. That's going to be 4 electrons, and we have 4 more to go. Once again, hydrogen is filled on the outside, so then we need to go to the center, and we do put them on as dots. So we're going to do 2 and 4. Does have a charge, so some brackets and a negative charge there on the outside would be appropriate. Any questions on that one there? All right, then N2, I think, is next. All right, so N2, which is nitrogen, that is 2 times 5, which is 10 valence electrons. In this case, there really is no central atom because it's diatomic, so you just kind of line them up side by side. And we really do just follow the same sort of approach, even though there's kind of no central atom. We're just going to connect them together with a single bond. And at this point, that uses 2 electrons, and we have 8 more to go. So just like before, we'll distribute those 8 to the outside ones, which they both are outside, really. So 2, 4, 6, and 8 in this case. At this point, we have now put on there our 10 electrons. The nitrogen on the left-hand side is a little short as it has only 4 electrons there. So follow the same rules. We're going to make a double bond. So we're going to grab a pair of electrons here and bring it in. When we do so, we will end up with something that looks like this. Once again here, it did get that nitrogen on the left a little bit better. It's up to 6, but it's not 8. So in this case, we obviously need to go to a triple bond, and this is how nitrogen gets to a triple bond. It needs to bring those electrons in as well to triple bond this guy up. And now we do have something where both of those guys have now reached 8 electrons and the octet rule. Question on that there. So you can see, even if it's diatomic, you really could just follow the same sort of steps. It works in the end as well. Then we had SH2. All right, so SH2, sulfur is 6, hydrogen is 1, and there's 2 of them, so looks like 8 again. In this case, just like kind of the top one there, or the middle one. We're going to put sulfur in the middle, hydrogen on the outsides. In this case here, we'll go 2, 4, and then 6 and 8. That gives our sulfur 8 electrons in the middle. Each of the hydrogen have 2, so it is fine. We don't have to actually do anything with that particular one there. And lastly here, I think the last one that you had was CO2. And that is 4 plus 2 times 6, so that's 12, 16 valence electrons. Once again, carbon and oxygen are in the same period on the periodic table, carbon being further to the left, which means it is the least electronegative, so it should be the carbon in the center. Oxygen on the outside. Once again, single bonding everybody gets us to 4 electrons. 6, 8, 10, filling up the outside, 12, 14, and 16 at this point. And again, we can see that our carbon is short, so we're going to double bond. In this case, you can double bond on either side. We'll take a pair of electrons in to do so. And if you do that, you'll end up with something that looks like this. And at this point, we are still short for the carbon. So we cannot obviously, well, you could triple bond to the right if you wanted to, but it's probably not the best idea to do that. And we'll talk about it in just a second, but you could actually make another double bond here. So usually the good approach is, if there is an opportunity to make another double bond to try to fix the situation, you do want to sort of exhaust that process before you kind of move on to the triple bond. So we will make a double bond on the other side here to do so. And in this case, I'll just draw it up here. We will end up with something that looks like this. And at this point, we still have only 16 electrons, but actually double bonding on both sides, we do reach the octet rule there for everybody, and everybody's happy. So again, in most cases, kind of exhausting that double bond before you move on to the triple bond, if possible, is really probably the best approach. Question on drawing Lewis structures. All right. So let's talk then a little bit about, these sort of options, and, how do you know maybe if one Lewis structure maybe is a better structure than another, or should you do this or do that, or kind of hook things up in different sort of orientation. One thing that sort of helps us make that decision when we're drawing Lewis structures is what is referred to as formal charge. So let's take a look at that. I think, there we go. So the formal charge on each element within a Lewis structure can be calculated. It's really the difference between the valence electrons in the free atom and really the sort of electrons it's sharing in the Lewis structure. So to calculate formal charge, you take the number of valence electrons in the atom that you're calculating for. You subtract it from the total number of non-bonding electrons. And those are the dots, right? So you're counting up dots. And those are individual dots, not pairs. So just individually, how many electrons that are non-bonding that are present. Minus 1/2 the number of bonding electrons, which are basically the lines in a Lewis structure. And you can do this for each of the atoms that are present in a Lewis structure. And as we'll talk about, it can really help you decide, between one Lewis structure and another, which one might be better. So let's take a look at a couple of Lewis structures here and sort of calculate the formal charges on each of these. All right, so if we had something like ozone and we drew ozone through our steps, we would end up with a Lewis structure that looks like this. Or if you just want to draw it straight out, it will look something like this. All right, so we could calculate the formal charge on each of these elements that are here. So we can calculate this guy, and this guy. We'll just call this 1, 2, and 3 since they're all oxygen. So if we were to calculate the formal charge for the first oxygen there, number 1, the number of valence electrons in oxygen is 6. In the first oxygen here, it has 2 and 4 non-bonding electrons, the dots, and minus 1/2 the number of bonding electrons, which are the lines. So that's 1 line and 2 lines going into it. So that is going to be 4 electrons as well. That's going to give us 6 minus 4, which is 2, minus 1/2 of 4, which is also 2. That gives us a formal charge for that oxygen of 0, basically, in that situation. If we go to the oxygen in the middle, the second one, that is 6 for the oxygen in the middle for the number of valence electrons it has, minus the number of non-bonding electrons, which is just these 2 right there, minus 1/2 the number of bonding electrons. So that's 2, that's 4, and that is 6 electrons, basically. Because 6 minus 2, which is 4, minus 1/2 of 6, which is 3. That's like 4 minus 3, I think. There you go. That is going to be a +1 type of situation. So that has a +1 formal charge there on that particular oxygen. And lastly here, if we were to calculate the formal charge for number 3, that has 6 because it's oxygen. In terms of non-bonding electrons, 2, 4, and 6 non-bonding electrons, minus 1/2 the bonding electrons, and that is just the line coming in. So that's going to be 2 electrons there. That is 6 minus 6, which is 0, minus 1/2 of 2 is -1. And in this particular situation with ozone, even though they are all oxygen, because of the way they are sharing electrons in this particular arrangement, they do have sort of different charges that they sort of take on in this situation. The guy at the end there takes on kind of like a 0 charge. The guy oxygen in the middle kind of takes on more of a +1 type of charge because of the way it's sharing electrons. And the guy at the far right there takes on a more -1 sort of situation in this case. If you add up all the formal charges, 0, +1, and -1, it does equal 0. And that's why it is neutral overall. But individually, as these guys sort of bond together in this arrangement, they sort of take on that sort of charge that you see in that particular case. Question on how to calculate formal charge there. All right, why don't you do CO3 2-, which I think is what you have next. And if you go through the Lewis structure drawing, you will end up with a structure that looks just like that. So calculate the formal charge on each of the elements that are there. Okay, let's take a look. So we'll start with the single bonded oxygen. Why not? Something like this. So this would be 6 minus 2, 4, 6 minus 1/2 of our bonding, which would be 2. So it's going to be 0, going to give us a -1. So that guy's got a -1 formal charge. This oxygen is identical, so it's actually going to come out the exact same. Obviously, if you do it the exact same way, 6 minus 6 minus 1/2 of 2 is -1. If we look at our double bonded oxygen here, we have 6 minus 2, 4, minus 1/2 of 4 as well, 1, 2 for each of those single bonds. This can give us 6 minus 4 is 2, minus 1/2 of 4, which is also 2. That's going to be 0. So this oxygen up here has a 0 formal charge. And if we look at our carbon, it's got a double bond happening there and some single bonds happening. So carbon is 4 valence electrons. It has no dots or non-bonding electrons, so -0, -1/2. Each of those lines represents 2 electrons. 8 gives us a 0. So the formal charge here is 0 on the carbon. And that is where the -2 comes from for the carbonate. Each of those oxygens that are single bonded basically are having a -1 charge happening there. And that's why carbonate has a -2 overall charge. Again, it's really a product of how the electrons are being shared in that situation as to how that ends up with those charges. Obviously, this is carbonate, which was the one we kind of skipped over. But again, if you drew your resonance structure for any of these guys here, like this, looks like this, it will be the same formal charge no matter which way you go there in this particular case, or even if you did it obviously with the double bond going the other way. So again, this is one of those guys you could draw the resonance structure for. And if you did the formal charge for any of those resonance structures, you would end up with the same overall result there in each of those cases. Any questions on how to calculate formal charge? So really, a lot of times what formal charge is used for is in a situation where maybe you are drawing some Lewis structures and maybe you want to decide, should I like triple bond it? Should I double bond it? Should I connect this element to this guy, without maybe connect to something else? It can really help you in a lot of situations choose perhaps a better Lewis structure than another. So you can draw some Lewis structures in some different ways, and some are better maybe than others, and some you shouldn't do at all. But it can actually help you decide, which Lewis structure might be better. And these are some of the main sort of things that you want to look at when you're sort of trying to decide between two different structures, maybe which one you should do. For neutral molecules, a Lewis structure where you have no formal charge is preferred. So basically, if you can draw a Lewis structure where you kind of zero out everybody in terms of their formal charge, all the elements that are there, that's sort of the best situation, is or try to zero out as much of the elements in a particular structure when you calculate the formal charge. That's usually sort of the best sort of situation. Usually if you draw Lewis structures where you end up with elements that have pretty large sort of formal charges like 2s and 3s or even higher, those are probably not the best structure, and you really shouldn't draw those type of structures. Now, if you're choosing between two Lewis structures where you have sort of a similar distribution of formal charges, the one that's probably the better structure and the more plausible structure is one where you end up with a negative formal charge on the more electronegative atom. So for example, if you have some distributions where it's like +1 and -1 and +1 and -1 in the other, but the -1 is on a more electronegative atom and say the structure on the right versus the guy on the left, then probably that's the better sort of choice. So to see sort of that in play, let's say we had something like formaldehyde, we weren't really sure how I want to connect it, and you end up with these two structures. Use formal charge to decide which one is better. And then let's also do one that we drew before. Let's say we drew CO2. Which one would be a better structure if you decided, hey, I would like to triple bond instead of doing some double bonding? All right, so see what you come up with. Use formal charge to decide between these two, and use formal charges to decide between those two structures. Okay, so since we're getting in, let's take a look and see. So we'll start with the structure on the left here between these two. So we'll do the single bonded hydrogen. So hydrogen is 1 valence electron -0, as there's no dots, like there should never be really. -1/2 of 2, which is our bonding electrons there. So that's going to be 1 - 1 basically, which is 0. So this hydrogen has 0, And if you do it for this hydrogen, it obviously will come out the same because it's the same bond. If we look at the carbon there, we have a carbon with a single bond, some dots, and double bond on the other side. So carbon is 4 minus 2 non-bonding electrons, minus 1/2 of 6, which is our double bond and single bond together, gives us 6 electrons. And that's going to give us 4 minus 2, which is 2, I believe, minus 1/2 of 6, which is 3. So 2 minus 3 is minus 1, should end up with here. And if we end up with the oxygen there in the middle, double bonded oxygen with some dots and a single bond on the other side, it's got 6 for oxygen, it has 2 non-bonding electrons, minus 1/2. Once again, here we have a double bond and a single bond, which gives us 6 total bonding electrons. It's going to be 6 minus 2, which is 4, minus 3, basically. It's going to be a +1 situation here. So in this arrangement, if you decide to kind of hook it up like this with the hydrogen on the other end, we do end up with a 0, -1, and +1, and 0. Now, if we do the same thing for our second structure here to compare, again, our single bonded hydrogen should come out the same. So it's going to be 1 minus 0 minus 1/2 of 2, which would be 0. That's going to be 0 and 0 for that guy. Our carbon in the second structure has 2 single bonds coming in and a double bond, which means that's going to be 4 minus 0 minus 1/2 of 8 for each of those bonds that are present. Gives us a 0 in this case. And our double bonded oxygen here looks something like this, which would be 6 minus 4 non-bonding electrons, minus 1/2 of 4 from the double bond, gives us 6 minus 4, which is 2, minus 2, which is 0. That is 0. So based on formal charge, the right structure here should probably be the one on the right-hand side. Yeah, this basically has a 0 formal charge for everybody. That's sort of the best situation. It essentially means that the electrons are really being shared not so unequally, right, on there. In addition, the guy on the left there, the -1 and the +1, those formal charges, actually the plus formal charges on the more electronegative atom, right, the oxygen rather than the carbon. So that also is not such a great situation. Any questions on that one there? All right, so earlier we drew the CO2, and I said earlier you could, if you want to, perhaps triple bond it instead of double bond. And let's see if it is a good or bad decision to do that. So let's see here, we'll start with our double bonded oxygen here in the top guy. So our double bonded oxygen going to be 6 minus 4, minus 1/2 of 4 for the double bond gives us 0. So that oxygen there is 0. That oxygen there is 0 in terms of its formal charge. We did the double bonded oxygen in the middle. That's going to be 4 minus 0 minus 1/2 of 8 from all the bonds. And that gives us 0. So that is zeros all the way across there in that structure, which makes me think that's probably a pretty good one. But let's take a look at this one here. Our single bonded oxygen going to be 6 minus 6 minus 1/2 of 2 for the bond that is here. That is going to give us a formal charge there, a -1 for this guy. The carbon in the middle got a triple bond and a single bond happening, 4 minus 0 minus 1/2 of 8. So that's going to be a 0. And now our triple bonded oxygen, which you don't really see too much, that's going to be 6 minus 2 minus 1/2 of 6 for the triple bond. 6 minus 2 is 4, minus 1/2 of 6 is 3. So that's going to give us a +1. So out of the two, the double bonded on both sides clears up 0 formal charges for everybody. And that is definitely a better structure than triple bonding it. And this is why we talked about earlier as well. Again, sometimes it's not a great idea to just double bond and triple bond out of the box. It'll sometimes not lead you to maybe the best structure. And if you ever want to kind of check your structures, you could calculate the formal charges and make a pretty good comparison based on formal charges. Any questions on formal charges? All right, we will wrap it up there for today.